This is from the section in our book titled Proportions in Triangles. Specifically, this is the Side-Splitter Theorem. It's a pretty easy corollary of just basic similar triangle stuff, but let me go through it because there is one cool bit of it that goes back to basics of proportions that we didn't do a lot of, and I'd like to focus on. So here's what we're given. We're given a big triangle QXY, and then it's called a side splitter because there's another segment here. It's RS that is splitting QX and QY, and specifically is parallel to this base XY. So it's crucial that these are parallel. So anytime you have parallels, you have a lot of angles that are going to be equal. You're almost guaranteed to have similarity. And so we've seen that kind of in the abstract, but now we want to see it as a calculational tool. So what do we get in the abstract here in terms of a similarity statement? We know that angle QRS is congruent to QXY, and QSR and QYX are congruent. Okay, and let's give a reason by corresponding angles, or sometimes people call that same side parallels. Okay, and also issing on the cake, it's not absolutely necessary. You just need two of these three, but angle Q is shared between QRS and QXY. And if you think QXY kind of looks like a scaled up version of QRS, you bet we've got a similarity. And that means that QRS and QXY are similar. Yay. Okay, so now why would we care? Well, it gives us all kinds of proportions, and if we know some of the sides, we're going to go and know other sides by similarity. We'll work through a couple examples of that. But the first thing is that there's just a little bit of a non-obvious thing we do. We get the simplest proportion would be XQ over RQ. Let's see if I can put this on the same page. XQ over RQ, let me make this a little bit tighter, equals Y, so XQ over RQ is YQ over SQ. So the whole left over the top partial left is the whole right over the top partial right. Just straight up corresponding sides are proportional from the similarity. So I have it in words here. Left whole over top left part equals right whole over top right part. But what the side-splitter theorem does is it just does a little bit of manipulation with a proportion to get a correspondence of parts with parts. What if we don't actually care about XQ, the whole thing, and YQ? We want to get a relationship between the bottom left, the top left, the bottom right, and the top right. We can totally do that. So let's do that. We'll just do a little algebra with this guy. Okay. And this is, oops. Is a standard. There's various ways to do this. These are sort of memorized. You can memorize these manipulations of proportions, but it usually amounts to adding one or subtracting one. And so I'm going to take this, which is the whole over the part. That's going to be some number bigger than 1. And I'm going to say, well, by what, how much over 1 is it excess? Or in other words, you could say is like I'm subtracting 100%. Because often intuitions are good if you think about percentages. So I'm just subtracting 1 from both sides. Now I'm going to put them both over a common denominator. So let me just sort of copy that and rewrite it. So I'm going to write that. Anytime you have fractions and sums or differences, your natural instinct should be to put everything over a common denominator. Okay, that allows me to combine. So it's XQ minus RQ over RQ. And we'll go back to the picture in a second. YQ minus SQ over SQ to see. Okay, so XQ minus RQ, what is that in the picture? That's the whole XQ minus RQ. Oh, that's the other part, XR. We've seen that a few times in some of these problems. Whole minus one part is the other part. So that's just XR. Okay, so let's rewrite that as XR over RQ. And then the other one, denominator still SQ, YQ minus SQ, that's the whole minus the top part. Hey, that's a good way to extract out the bottom part, that's SY. Oops, that's a Y, there we go. Or in words, we already got it written out here. The bottom left part over the top left part is the same ratio as the bottom right part over the top right part. So when you've got two segments split by parallel lines, whatever relationship that this bottom looks like, this is in this picture, like maybe this bottom is like 2/3 as long as this guy, it'll be guaranteed that the same is true on the right, at ys would be about 2/3 as long as this guy. And it came from a statement that mentioned the whole, but we took the whole out because a lot of times you only care about the parts. So let me show you two quick examples of that. Here's example one. Very, very similar kind of thing. I just turned it around a little bit. I stole this example. Actually, I stole a lot of this video from Ms. Petrillo. So I'm kind of redoing it in my own words. So here we know a part and a part and a part, and then we want one missing part. We don't really want to have to deal with the whole, although we always could if we just forget the side splitter. But side splitter is a really good tool when you know some parts and want to get other parts and you want to ignore the whole. Okay, so it just says we're just going to get x over 9. That's the appropriate ratio of part to part in one side, and that's going to equal 2 over 6. Hey, that's 1/3. X equals 9 times 1/3 equals 3. Yay! So 6 is to 2 as 9 is to 3. That is our proportion. So that would be the simplest example. Slightly more complicated setup and a little bit more complicated in terms of the algebra we get, but not a lot more. It's going to have two x's in it. Here, notice I don't have anything explicitly marked as parallel, but I know that KF is perpendicular both to FG and to HI. So in fact, HI and FG are parallel. As I've drawn it, I'm suggesting that FK is vertical. And surprise, surprise, two things that are perpendicular to that are both going to be horizontal, and they're going to be parallel. Once again, that activates side splitter. And what are we going to get? 2x plus 1 over 8 equals 5x minus 1 over 16. Okay. Or if you want to, you can always switch those the extremes of means. You could always say that 16 over 8, that's how much longer the right-hand part is than the corresponding left-hand part. That's a 2-to-1 ratio. Hey, that's nice. Is the same as how much this right-hand part on the bottom floor, if you think of this like a building, what the proportion is, what the ratio is between that and the left-hand side. So either way works, okay? I'll just go ahead and riff off this second one since I just wrote it down, and I'll just cross multiply. I get 4x plus 2 equals 5x minus 1, and I get 3 equals 5x minus 4x. Hey, that's x. So x equals 3 again. Okay. So no matter how these guys are marked with x's and things like that, you're going to be able to write a proportion, and then you're going to be able to solve it. Sometimes it'll be a quadratic. We'll see that in the next video.